right, coming back in, you guys just lose my smiling face this morning because you're not going to be able to see me. I couldn't get the technology to work with the two computers, so we're going to one, so you're only going to get the actual notes that are there. So you miss my expressions as we go, but that's okay. You'll survive on this. So let's define the multiplicity of the zeros. So now if you look at our graphs and our polynomials that we were looking at before, that are zeros, and we're going by looks like. And looks like is not the best way to find the zeros of a graph, but for what we're doing in this investigation, this is kind of exactly what we're going to do. But let's define multiplicity of a zero. And I've kind of talked about that a little bit before, so we're just kind of bringing that back in. So the multiplicity of a zero, so let's say if we had a function, if x equal to a is a zero, aka x-intercept of a polynomial. And it doesn't really have to be a polynomial. We're just talking about polynomials right now. So that's one of those things where any function in general, maybe I should just say any function, but it really is, because we're in the polynomial section, I'm just going to say polynomial. So if you have a zero of a polynomial and the factor corresponding to that zero, which we know is going to be the factor x minus a, occurs p times, I don't like p, let's use occurs k times, then x equal to a has a multiplicity of k. And what we really mean by that is, if you think about the polynomial, we've seen some examples of this before. If I had a polynomial, so I'm just going to do a little example over here. If p of x was negative 2 x minus 3 cubed, x plus 1, and x minus 2 squared. So if I had a polynomial like that. And so if we were looking at it, we would say that our zeros are going to be x equals to 3, x equals to negative 1, and x equals to 2. And so in looking at that, the 3, notice that the 3 occurs a factor 3 times. So we would say that x equal to 3 has multiplicity of 3, that the power on the x plus 1 is going to be 1. So again, the multiplicity of that one is going to be, has a multiplicity of 1. And because the power on the x minus 2 is a 2, then we say that that has multiplicity of 2. And so that's kind of what we're talking about with the occurs in the polynomial k times, is how many times you have that factor listed there. All right, now we have some information here below that we want to talk about with the polynomials. All right, notice that in the graph of f of x, I am telling you that all of the zeros have a multiplicity of 1. So they occur exactly once. Now what we want to do is we're looking at kind of what's happening each time it occurs once. So it's here, here, and here. We're kind of looking at what the graph is doing at the 0. Okay, and I'm telling you that for f of x, they all occur exactly with multiplicity of 1. Then for g of x, the 0, negative 2.5 has a multiplicity of 1, right? But x equal to 2 has a multiplicity of 3. So let's come up here and let's look at the negative 2.5. And let's look at the behavior as it hits that x-intercept there versus the behavior over here, where this one was the multiplicity of 3. Multiplicity of 3, multiplicity of 1, and at all of these, we had a multiplicity of 1. All right, so now, if I was, before I read down and read what's below, if I were guessing of the zeros over here in the graph of h of x, what would you think about the 0 here at -4? What do you think the multiplicity of that is? And what do you think the multiplicity of -2 is? And what do you think the multiplicity of 5 is? If you compare that to kind of what's going on over here, hopefully you would say that all three of those, since they kind of look very similar to what was going on in f of x, hopefully you'll guess that they have a multiplicity of 1. But now notice here at 2, this has a very different behavior. So let's scroll down and see what it says about 2. So again, notice we said that the zeros, -4, -2, 5, have a multiplicity of 1. But now 2 has a multiplicity of 2. So that, and notice the behavior is different there, kind of looking at it. So that has a multiplicity of 2. And so what we want to be able to do is kind of make this connection between what we know the multiplicity is and what we see occurring on the graph. All right, so let's go down to the next page. Now, one thing I would like you to notice is let's talk about the sum of the multiplicities of the zeros and the degree of the function. So let's look at f of x first. All right, now for f of x, we had all the zeros had a multiplicity of 1. So if we look at it, we had 1, 2, 3 zeros, and we had a multiplicity of 1. So 1 plus 1 plus 1 equals 3. Now, also, going back to what we learned about polynomials and behavior like that, if I come back up here and look at this, let's talk about the behavior of the graph, which is something that, since we're reviewing, you might not remember. So if I look at this function, okay, the first thing I'm going to notice is that this function has two turning points, two relative extrema. And we'll remember that the degree minus 1 is going to equal the max number of relative extrema, or terms, in a polynomial. And so that's one thing to notice and kind of remind ourselves. We also have 1, 2, 3 x-intercepts. So the degree equals the max number of x-intercepts. It could be, there could be less x-intercepts than the degree, but the degree has to be larger than the max number. So if I was looking at this graph and just saying, could I guess what the degree of f of x is, just based on those two facts, we're definitely going to say that we think the degree is at least 3. So the degree of f of x is most likely 3. And that's kind of one of the things that we want to look at. Now, the reason why we say most likely 3, this has to do with where we're talking about real zeros versus complex zeros, which you would have talked about in Algebra 2. When I'm looking at the x-intercepts, these are the real zeros. And we haven't really talked about complex zeros yet, and that's going to come in a later section. So right now, we're just going to assume that these polynomials we're looking at does not have complex zeros, okay? Which will add an extra thing going on that you won't exactly see in the Cartesian plane, which is the real graphing system. So looking at this, the degree is most likely 3, and I'm going to just put over here on the side, assuming no complex zeros. All right? And then let's look at, of course, I didn't really leave enough room here, did I? Let me move this around just a little bit so that we can do h of x and g of x as well. So I'm just going to take this and put that there. And don't get mad at me because you guys are, trying to fit this in too, but you can erase as well. All right, so let's look at the next one up here. So now we have our g of x. And again, g of x, if I was looking at this one, right, we had a multiplicity of 1, and we had so we had 2 real zeros, and we had a multiplicity of 1 and a multiplicity of 3. So let's kind of list that down. Let's do this one in green. So g of x, we had a multiplicity of 1, we had a multiplicity of 3, and that's 4. Now, the degree of f of x, okay, what do we know? Well, when I look at the g of x function, because of the multiplicity and the number of factors that you have, I know that the degree has to be at least 4. I also know because the end behavior, both ends are going up, that it's an even degree. So let's talk about that. I didn't talk about it with f of x, but if the ends are opposite direction, okay, they go in different directions, then we know the degree is odd. And if the ends go the same direction, then we know the degree is even. So there's a lot of stuff that we're learning about our polynomials, kind of reminding you of things that are going on. Now, I obviously know here in g of x, even though I only had 2 real x-intercepts, I know that that's not a quadratic. And the reason that I know it's not a quadratic is because of the fact that I have a multiplicity of 3. Do you see here where it crosses right here? It's got a point of inflection there. And I say it looks like a cubic, where it has that nice little flat leveling off point of inflection. And so that idea there, and we also know that in the formula for this, we would have our x minus or plus 2.5 as a factor, and then we would have this x minus 2 as a factor 3 times some kind of a coefficient in front. We don't know what the scalar factor is on it. And then we have our g of x. And that at a minimum, again, assuming no complex zeros, that we would have to have at least a 4th degree polynomial there for g of x. So down here, again, notice that the multiplicity, if we add that up, and again, assuming no complex zeros, the degree of g of x is at least, we have to say that, at least 4, and it's even, and that's, of course, assuming no complex zeros. For this one, I feel like I'm just kind of moving things all around here for you guys. Since I'm assuming no complex for all of them, let's just put this up here so that we have it. And then I'm also going to add in, let's do, instead of most likely 3, let's do at least 3 is, English language, is at least 3, and we definitely know that it is odd. Okay? And again, we're assuming no complex zeros when we're looking at it. All right, so let's take a look at h of x, our last one there. I'm just going to change this back to black. And so on that one, what did we have? We had the zeros. We had 3 of them that were singles. So 1 plus 1 plus 1. And then we had one that had a multiplicity of 2. So that's going to equal 5. All right, so let's go take a look at our graph of that one. So in our graph of that one, let's kind of see what we have going on here. Okay, notice the ends are going in opposite directions. So the 5 makes sense in that it's odd. We count the number of extrema, 1, 2, 3, and 4. So again, that degree minus 1 is the max number of extrema. So 5 makes sense. So we know it's at least 5. And again, that's all assuming that we have no complex zeros on this. So the degree of h of x is at least 5, and it's odd. And again, assuming no complex zeros. All right, so now let's take a look at